Hello everyone. Welcome to my talk on reliability engineering for inference serving. As you probably know, and I agree with everything Mariam said, which is there's so much shift happening in inferencing itself. Right now, if anybody's putting on inference pipelines in production, the big problem is how do we make them reliable? And that's an important question, which I've been thinking about a lot, and it's a lot to do with the work that I've been doing over the past couple of years. So I am the ex-founder and research engineering lead for Abi Aryan. Right now, I'm in an advisor capacity with them. My job was essentially building the infra platform for an agentic system. So I developed an in-house agentic system observability library specifically for this kind of work. Um, and one of the main reasons for this was there's a lot of existing tooling that assumes stateless request, but there's not enough good tooling out there for stateful request structures, which is what your agentic systems are working on. Outside of that, I'm also doing a doctoral degree in SLO adaptive inference systems, working on compilers. So that's a little bit about me. I have a book which came out. So the LLM Ops book, I wrote that, finished it in 2024 December. So it's a little bit outdated, but it's nice to see. Okay, you can possibly track where I'm coming from, which is from like a very observability kind of mindset itself. And right now I'm working on a book called GP Engineering, AI Inference and Systems Design, which is finishing up next month and it will come out in September this year. I teach a course on Raven. Anyway, we'll talk about that later. Let's go on to the actual talk itself. So today's talk will be in three parts. One is why is reliability hard? Second thing is how is inference changing? Because you would hear this, the entire industry is shifting and it's shifting so quickly. It's very hard to be able to figure out where it's going. So I'll try to address the second part. And the third thing, what you want to measure within your inference pipelines right now and going in the future as well. So when we talk about reliability, the first thing is what is actually reliability? It's a very, you can call it an art, you can call it an engineering, depending on where you're looking at. I like to call it an art because, again, you can't buy code into this. There has to be a lot of pattern recognition you've done over a period of time. Oh, but the key goal in reliability is there are going to be failures. They're literally inevitable. There's going to be complexity because this complexity comes from distributed systems, which creates these nonlinear interactions as well as cascading failures. There's going to be trade-offs, and this is the main play which makes reliability really hard. But reliability engineering is not really about preventing a failure. That's literally impossible. You can't prevent it. It's about designing systems that can continue delivering predictable outcomes, especially when failures are going to happen. So it's about being prepared, not about curing every single thing out there. But the main challenge in modern distributed systems is there's so many trade-offs between performance, availability, as well as cost. So how do you keep all of them front and center at all point in times? And AI inference systems basically inherit all of these challenges, plus they add all of the challenges and failures with GPUs itself, plus with long-lived states and agentic execution on top. So it becomes a slightly more complex problems than we've seen till date. But I can tell you this, this is not a new problem. Most of the problems that you're seeing in inference systems have been here for the last couple of years. So this is a very common thing you would have seen, which is there a pipeline ends up breaking and the ML intuitions will basically say, or ML engineer on the team will basically say, this makes no sense, we're well into capacity. And the infra engineer will say, well, something is holding my memory hostage, which is memory has essentially become a reliability concern. This is not a new problem. Once again, I've taken 3 or 4 case studies to give you a very good idea on where have we seen all of these problems before. So the first case study is Hadoop versus Spark. So the big data world, people who are very old in this room from like pre-2014, 2015 world, you would have remembered this, which is how Spark was originally sold. They said, well, you're going to have the same data, you're going to have the same cluster, and it's going to be much faster than using Hadoop. Well, part of that was true, but there was a hidden change, which is it was not that easy. Why? Because MapReduce or Hadoop basically treated execution as disposable. If any task failed, you just restarted it. So the failure was cheap. What happened when we introduced Spark was now these executors basically held state, which is your RDTs lived in memory. So the partial progress that you were making suddenly had value. Now, a single inference request still behaves very much like Hadoop systems. You do the work, you return the result you want. But the modern inferencing systems, especially the inferencing systems with agentic AI that you're seeing, more and more of starting from mid of this year, you'll see more of them in the coming few years to come. They behave more like Spark as compared to like Hadoop, which is there's long-lived execution, there's persistent states, the resources will stay allocated far longer than we expect. So what's the lesson here? First lesson that you want to take away is when execution becomes stateful, the reliability assumptions are going to change. So what worked for inferencing pipelines 2 years ago is not going to work for inference pipelines right now. The second case study. Again, some people would remember this as well, which is the Lambda functions. Well, initially we were relying very heavily on Lambda functions within cloud computing itself. And what happened was somewhere around 2010, AWS teams basically moved towards orchestrated work. When you would have seen this come up more often in 2016, 2017, which is we started going towards step functions, towards Airflow, towards temporal or Argo, basically the workflows. So what these workflows did for you was something very similar, which is the failures were no longer cheap. The retries were compounded across stages. Every single time you made any partial progress that stayed alive in the system, you got this zombie workflow. So it was still running, it was still costing money, and it was not doing anything useful. Does that sound very similar to you? Yes. Well, that's agentic systems for you. So lesson number 2. What works for stateful systems completely breaks for stateless systems. The third one, which is simple queries versus database transaction. If you work with SQL, you've seen this as well. So as we move, as this move was happening in the industry, which is as the database engineers were moving towards database transaction, essentially, the same lesson sort of got repeated, which is a simple query was easy to operate. It ran, it completed, it failed, you retried it. The cost was predictable, the failure was manageable. Now compare that to a long-running transaction, and these long-running transactions are very similar to the self-running agents, you could say, or the agents that are trying to choose between should I trigger up a web search right now or should I call up another tool? This is essentially a workflow. So the progress you're making starts to matter, and that's when everything changes. A failed query is basically an inconvenience, but a failed transaction that can become a system-wide problem. The same lesson here, which is an agent is much closer to a transaction. It plans, it accumulates context, it calls tools, it maintains intermediate state, and it invests in compute over a period of time. So just like transactions, the most expensive failures will most likely happen near the end, never in the beginning. If an agent spends 60 seconds reasoning, making 20 tool calls, and ends up burning 100,000 tokens, and then it fails, when you've already paid the bill. The work is gone, the cost will remain in your ledger for the next quarter at least. The moment this progress becomes valuable, the priorities that we have in reliability engineering, they become much more complex. Because stateless systems, they care about successful requests, but stateful systems, this is the main thing you want to take away with yourself, which is anytime you're trying to design any stateless system, that just cares about successful requests. Any observability platform you're looking at right now, or any tracing platforms you're looking at right now, they're designed essentially with this idea. But stateful systems, they care about preserving progress. And the reliability ensuring that you're going to do for them is going to be about treating progress as a reliability problem. The fourth thing, Kubernetes. Again, maybe if some of you have probably worked in Kubernetes, you would have seen that, which is one bad reconciliation becomes thousands. The APIs get hammered, your clusters become unstable. Well, Kubernetes didn't fix this by making controllers smarter. It added guardrails, which is it added backoff, it added rate limits, it added item potency, it added convergence guarantees. The entire smoothing the world of reliability engineering. Now let's look at agents. We're trying to do exactly the same thing. So our loop looks something like you're doing some observation, then the agent is trying to decide, making a tool call, updating the state, and repeating the entire process again. The only difference is the policy engine, in this case, is a large language model. And the side effects, well, those will cost you GPU time as well as API calls. So just like a bad controller was burning in API capacity, a bad agent burns the GPU capacity. A bad controller was something that ended up never converging. A bad agent is something that never finishes. Same identical problem, which is think of agents as reconciliation hubs with a GPU budget. And every agent, what it does is it becomes a control plane problem. And that's the mental mindset that you want to look at agents. Now, traditional inference, or the inference that we were seeing, or you would still see, there's two kinds of job posts that do exist right now, which is there will be something called inference engineer, and a lot of work will be around quantization. A lot of work will be around the training side. I still call that traditional inference. And the second kind of inference that is coming up is more around agentic inference. These two inferences are very different. The way I look at it is inference as a pre-deployment concern and inference as a post-deployment and serving concerns. Both of them will have different reliability metrics. And today I'll talk about the later, which is the post-deployment one. So how is it essentially changing? Well, look at this comparison in front of you. So look at the traditional inference on the left. You have a request that arrives in your system, the model generates an answer, the request is completed, the state disappears, failures are achieved, your cost will always be counted. Now look at what's happening within the agentic inference itself. Your execution becomes long-lived, your state is going to persist, your progress is going to accumulate, tool calls will clear dependencies, and failures will happen towards the end, after the work is already done, after it has already made a lot of calls. So the cost will accumulate even before you know something went wrong. So the capacity planning suddenly turns nonlinear, and it's not a model problem anymore, it's an execution problem. So what you're looking at here is a stateful distributed system where the control plane happens to be powered by a large language model. Once you see it that way, every single failure mode starts looking very similar for you. Now, the reason I say this is traditional inference was basically asking questions. So when you build a RAD system, for example, we're still in the traditional model. We're retrieving the context, we're augmenting a prompt, we're generating an answer, and the request end. The state disappears. Even advanced RADs, mostly they're answering just a question. And that's the reason I'm calling it agentic inference, because the way RAD systems are designed versus the way agentic systems are designed is very different. And the kind of priorities each would have would be very different as well. Now, anytime you're doing agentic inference and your agent basically decides to continue or to loop, you're executing a program. And once you do that, you're introducing loops, you're introducing branching, you're introducing long-lived state, you're introducing external side effects. So the problem is really not just that, oh my God, LLMs are unreliable. No, they're super reliable. The challenge is that execution has always been harder to make reliable than inferencing. So what we're building is basically we're building systems that can execute instead of infer. And that's the priority shift that is happening right now. So that's the main reason why latency, cost, and failures, they all behave very differently than they used to. We're no longer thinking about just, we have a model and we're trying to serve predictions. No, we're serving long-lived execution programs that are running on top of GPUs. So when you have, I think it's a very good way to visualize it in terms of how every single error across every single stage ends up compounding. So the challenge isn't any one step on its own. The challenge is basically knowing that every step and every layer would have a probability of failure. Every dependency will have its own latency. Every external system will have its own availability profile. So what matters now is that you're looking at reliability as across the layers, across every single dependency out there. So the execution graph, that's the where you're looking at inference serving reliability problems. It's not one state, but the entire surface area of an execution graph from beginning to the end. Now, why is that important? Well, the first thing is, even if you build up, like, let's say, an observability platform on top of it, most of the observability platforms still talk in averages, which is, let's say, time to first token, or this is your P50 latency. One of the things that really most of the data scientists here and most of the SRE people will tell you is that averages do lie. Your P50 can look fantastic, but the users will still end up being miserable. So in traditional inference, latency was mostly a user experience metric, right? But in agentic systems, your latency is also a capacity metric. And why do I say that? Because every additional second of execution will increase the amount of state your infrastructure must keep alive. And once that starts happening, reliability is not just an execution problem, it becomes a queuing problem very quickly. So this is the first thing you want to take. Maybe the second thing I've already said, there's a first thing, which is latency will create concurrency within your system. Why? GPUs are not servers, and they don't behave anything like servers. In traditional systems, we used to obsess over CPU, network, memory. With GPUs, the real constraint is often memory, not just compute itself. So the GPU can look perfectly healthy and still be unable to accept new work. That is the queuing problem that we've been talking about. Why? Because capacity is being consumed not just by computations itself, but by the state. So there are three big reliability changes that you have in these new agentic systems. The first thing is, think about it this way, which is latency always creates concurrency. When your requests are taking longer. So there's this guy, he was one of the scientists, I think, probably at MIT, and he created this law. His name is John Little. So he created this law, which became very popular as Little's law. So what he basically said is, the queuing theory states that the average number of items that live in a state is equal to the average arrival rate multiplied by the average time each item spends in the system. And you would have seen that. So, for example, if you've been studying a lot of lead code problems or data structure problems, you would have seen these exact problems in execution itself. So now coming to inferencing, it's very similar. So you can take the Little's law and apply it over here, which is every concurrent run will be approximately equal to the arrival rate and the execution time of the previous query itself. And why does that matter? Because when requests take longer, for whatever reason, maybe your agent was planning, maybe it was doing tool calls, maybe it was just waiting, or maybe it was just maintaining the state itself. If you have more requests, those will overlap in time. So the most concurrent in-flight work would mean more KV cache and more session rate must be held simultaneously. So unlike a web server where a GPU at 3% utilization can already be a bad agent away from like an OOM. So the resource we're managing isn't just compute anymore, it's state. That's the first reliability metric you have to think about, which is the state is the main problem. So how do you look at the state? Well, we look at the execution graph. The second thing is the partial progress. So the partial progress is, of course, generated by the state itself, but it's a state management problem, which is how do we make sure that the KV cache is not creating more pressure on the system than is necessary? That's a reliability risk that we're talking about. Now, the reason for this, I think you would have seen this the dashboards do lie. And right now I can say this very comfortably. I've not really seen good GPU tracers that are close to reality itself. Most of the tracers are very, very bad, and they're very isolated, which is they show you just what's happening on the GPU side. I've seen other tracers that will tell you what's happening on the request side, but they don't combine everything together. And that's what's missing in terms of being able to debug these agentic inference pipelines, which is having an end-to-end execution graph and being able to see once very quickly where the problems are happening. So the question you're looking for isn't really how busy is my GPU, but the question you want to ask is how much state is my GPU carrying? Now, those are two very different reliability questions. Most of the people in the industry are still asking that first question, which is how busy is my GPU? Is that, let me try to optimize that? No. What you want to ask about is how much state is the GPU carrying? What's a good time to to remove that state or to maintain that state? How long do you have to hold that state itself? That's the reliability problem that you would be looking at in the next years to come. The third thing is cost is a reliability metric. Why? Well, I think it's pretty obvious to say if you have a system that you cannot afford, it becomes an unreliable system itself. So the first system isn't really an outage. It's basically unaffordability, which is the cost maintenance side of things, because every token has a price. Every retry has a price. Every second of execution has a price. So reliability is no longer just about protecting uptime. It's about protecting token economics. So what are the new SLOs that you should be thinking about? Well, then for the traditional systems or for most of the observability tools you would see out there, what they're still looking at is availability, latency, error rates. No. For the new agentic inference systems, what you would be looking at beyond that is the cost per task, the task completion rate, the tool success rate, and the failure adjusted cost. And this becomes very important because if you don't measure it, it's very hard to be able to optimize it. So a successful request is no longer just the unit of value. It's basically making sure or knowing the economics behind a successfully completed task. And both of those are not always the same thing. So the best reliability teams that I've seen, what they're doing is not replacing the old SLOs. They're adding new dimensions that basically reflect how these systems are behaving in production. So what should observability do? Well, it has to evolve. It has to evolve to add visibility into all of these things. Visibility into cost attribution, visibility into tool execution graphs, into the token flows, into the agent traces itself. So if you've been using, I don't know, if you guys are building your own agents by yourself, and if so, what tracing tools that you're using, or if you're, let's say, using Logfire or QAI, then again, those are very, very limited. So they're not even combining the VLLM metrics, for example, or SGLang metrics with those ones. So right now, everything is basically sitting in silos. And we've spent years in the last 3 years, most of the observability tooling I've seen in this space is learning how to trace request. Now, what we need to do is to go away from request and start tracing decisions, because decisions are becoming the unit of execution. If the decision hasn't been made successfully, or if the decision took way too many tokens, and if there was a failure within that decision itself that the agent was supposed to make, that is a failed task itself. So how to measure this? Well, these are the 5 numbers that we would be looking at. But before this, most teams are still monitoring request, tokens, GPU utilization. I would say these are the 5 things that you need to add on top of those ones, which is what's the peak VRAM per concurrent run? What are the number of tokens per successful task? How much complexity are you introducing through the tools itself? How expensive your failure becomes when it happens. So together, as you are looking at all of this, what you do is you have a much better picture of the system health than the GPU utilization will ever tell you, irrespective of how good your GPU utilization dashboard or tooling or tracer is. So let's go through them one by one. So if you want to take away something, take a one screenshot from my talk. It has to be this one. And just because it looks like a comic. But this is one which you want to keep with you. So these 5 numbers, these are the same numbers we talked about in the last slide, but these will tell you what's about to happen, which is it will tell you when does the memory pressure become too much? How much will the real cost be? If there are too many people in the waiting, and essentially if your task becomes slow and if the system can no longer handle it, what is the system complexity like? What is the reliability waste? So all of these metrics, not one, not two, but all 5 of them together give you a very clear picture of your system altogether. So to wrap up, these are the reliability patterns that I'm seeing emerging. And the interesting part is none of these patterns are particularly exotic or new. These are the reliability engineering patterns that we've been used to for years. So there are 4 examples that I gave you, the 4 case studies that we talked about with the Kubernetes controllers, with the Spark. Every single team that worked on those solutions had exactly seen and adopted these patterns. So the first pattern is you need to budget over retries. The second pattern you're looking at is load shedding, which is not every request should be accepted. When your system becomes overloaded, protecting the platform is more important than attempting every task itself. The third thing is you need to do very aggressive context management itself. Unlimited context might sound super attractive, but it will very quickly become a memory problem. So the most reliable systems are the ones that are discarding the information intentionally and not keeping every single thing with them, because the state that you're holding within the system itself is a capacity problem, is the one creating the concurrency problem for yourself. The fourth thing is implementing circuit breakers around tools. And this is an idea you would have seen most likely around evals as well, which is in agentic systems, the weakest component isn't your model itself, it's the external dependency. One unhealthy tool can destabilize your entire workflow. And finally, what you need is the kill switches. So this one might sound very obvious, but many agentic systems still don't have a good way to terminate runway execution. Most of the cloud inference platforms don't have a really good way to terminate runway execution itself. So every mature execution platform eventually learns this lesson and starts implementing this itself. Because the goal here is this. The most reliable agent that you're trying to design, or the most reliable agentic pipeline that you're trying to design, is not the smartest pipeline itself. It's the best agentic pipelines I've seen are the ones that know exactly when to stop. And that should be the goal. Bounded execution, never perfect execution. If you can do bounded execution, reliability becomes an easy problem. So what are the final takeaways? If I had to compress every single thing that we talked about today into a few principles, here would be the 7 principles. The first thing is reliability is not just an uptime problem. A system can be available and still be unreliable. The second thing is if your latency is unpredictable, then the cost is going to explode. And your state will become the real bottleneck, not the flops, not the model parameters, but the state. The state in memory, the state in workflows, the state in execution graph. The state is what will limit your scalability. The third thing is latency is what creates concurrency within agentic pipelines itself. So this is one of the most important operational lessons in AI systems. The traffic isn't what is going to kill you, but your execution time is what's going to kill you. The fourth thing is concurrency will create cost. So every additional active execution that you're doing on your system is going to deplete your infrastructure. So reliability and economics, the token economics, they're basically the same conversation. Fifth thing is agents are execution systems. Stop thinking of them as model endpoints. Stop thinking of them as chat interfaces. Start thinking of them as execution systems, because execution systems need strong reliability engineering. The sixth thing that you should think about is think of GPUs as the stateful infrastructure, not accelerators, not just these devices that you have on your system, not faster CPUs, but what they are carrying is the critical execution state. And what needs to happen anytime you're carrying any critical execution state is you need to make it bounded, because bounded system will always outperform unbounded system. Every mature distributed systems team out there learns this one principle, which is you need to embrace limits. Limits on retries, limits on execution, limits on state growth, limits on resource consumption. And people who are building up AI systems in the future, and especially like inference pipelines on the serving side, they need to learn the same lesson very quickly. So while the technology might be new, while a lot of stuff that we're doing is new, but these lessons are not new. These lessons are familiar. The hardware might be different. The stakes might be higher. But the fundamentals are still the same. So that's my talk. So if there's one final thing I'll say is LLMs are system. Your performance lives in the boring details, not in the fun things that most people think about. Anyway, happy to talk about Q&A if you guys have any questions.